This video is brought to you by mywayteaching.com.
In this part, let us study what is this thermal equilibrium. Okay. See, in general, equilibrium in mechanics means the net external force as well as the torque which is acting on a system are zero. The term equilibrium in thermodynamics appears a little in a different context. We say the state of a system is in equilibrium state if the macroscopic variables that characterize the system do not change in time. In case of thermodynamics, these the macroscopic variables, for example, the pressure, you can take that volume, temperature, mass, all these are the macroscopic variables. If these macroscopic variables do not change with time, then we say that system is in thermal equilibrium. For example, a gas inside a closed rigid container which is completely insulated from its surroundings with fixed values of pressure, volume, temperature, mass, and composition that do not change with time. That is the perfect example of a thermodynamic equilibrium. Okay, a gas inside a closed rigid container. Completely insulated from its surroundings. That is the example. In that case, all the values, the macroscopic values of the system do not change with time. In general, whether or not a system is in state of equilibrium, it depends on the surroundings and the nature of the wall that separates the system from the surroundings. You just consider two gases A and B occupying two different containers. Okay, they appear, no, they occupy two different containers. We know experimentally that pressure and volume of a given mass of gas can be chosen to be its two independent variables. So let the pressure and volume of the gases be for this first gas in container A, pressure and volume be PA and VA, and for the gas in container B, we take it as PB and VB. Okay. Suppose first that the two systems are put in proximity but they are separated by an adiabatic wall, which is an insulating wall but that can be movable, that does not allow flow of energy from one to the other. So these two are separated with that particular kind of wall. So the systems are insulated from even from the rest of the surroundings by similar adiabatic walls, which means it is completely surrounded with adiabatic walls, so it is insulated from the surroundings. The situation is shown in the figure. You can see here, this is the adiabatic wall, this is also a adiabatic wall, and these two gases are separated with this adiabatic wall, and the gas is filled in the container. So in this case it is found that any possible pair of values, that is PAVA, will be in equilibrium with any other possible pair of values, that is PBVB, because it is completely surrounded with the adiabatic wall, and that macroscopic variables do not change with time. Suppose you just take another example. Adiabatic wall, we are replacing that adiabatic wall. We are replacing with the diathermic wall. What is this diathermic wall? Now we are replacing adiabatic wall with a diathermic wall. This diathermic wall is a conducting wall. Adiabatic wall, it is a non-conducting wall, or we can say insulating wall. But a diathermic wall is a conducting wall that allows energy flow from one to another. It is then found that the macroscopic variables of the system A and B change spontaneously until both the system attain equilibrium states. After that, there is no change in states. So you can see that in this particular. So here it is not an adiabatic wall, this is a diathermic wall. So in this case, since this is a conducting wall, the macroscopic variables in the container A and B, they continuously change until they attain an equilibrium state. After that, there is no change in their states once they attain that equilibrium state. The pressure and volume variables of the two gases change to PB dash, BB dash, and PA dash, VA dash, such that the new states of A and B are in equilibrium with each other. There is no more energy flow from one to another once they attain the equilibrium state. So we can say that system A is in thermal equilibrium with system B. Once that flow of energy takes place, and when they attain that equilibrium state, then the no more energy flow will take place. So at that time we can say that system A is in thermal equilibrium with system B. In thermal equilibrium, the temperatures of the two systems are equal, isn't it? When they attain that equilibrium state, the temperature will become equal. So now let us see the zeroth law of thermodynamics. Again, imagine two systems A and B which are separated by an adiabatic wall, while each is in contact with the third system via conducting wall. You can see that in the figure. See, A and B are no, they are separated with an adiabatic wall. They are in contact with the system C with the conducting wall. the states of the systems, their macroscopic variables will change until both A and B come to thermal equilibrium with the system C. After this is achieved, suppose that the adiabatic wall between A and B is replaced by a conducting wall and C is insulated from A and B. Reverse of that. So now this is adiabatic wall and the wall between A and B it is replaced with the conducting wall. We can say diathermic wall. So it is found that the states of A and B change no further, that is, they are found to be in thermal equilibrium with each other. So, what this observation says? So, this observation forms the basis of zeroth law of thermodynamics. What is that zeroth law of thermodynamics says then? Let's see. Zeroth law of thermodynamics says which states that two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other, which means in the first case it was in they attain the thermal equilibrium with the third system C, which means a and B will also attain the thermal equilibrium state at that particular state. Again, even though you replace the wall, again there will no more energy flow will takes place from A to B because they have already attained the thermal equilibrium. So two systems in thermal equilibrium with the third system separately are in thermal equilibrium with each other. So RH Fowler formulated this law in 1931, long after the first and second laws of thermodynamics were stated and shown on board. Okay, the zeroth law clearly suggests that when two systems A and B are in thermal equilibrium, there must be a physical quantity that has the same value for both. This thermodynamic variable whose value is equal for two systems in thermo equilibrium is called as temperature. So temperature will be equal as I told you before in thermal equilibrium. Thus, if A and B are separately in equilibrium with the C, then TA is equal to TC and TB is equal to TC, isn't it? Because they are separately in thermal equilibrium with the third system C. But this equation implies that TA is equal to TB, which means the systems A and B are also in thermal equilibrium. So now we have arrived at the concept of temperature. Formally via zeroth law, isn't it? From this zeroth law, we have arrived at the concept of temperature. So even though that both the systems A and B are in thermal equilibrium with the system C, it also means that the systems A and B are also in thermal equilibrium. So that is what this zeroth law says. And why this happens? This is because of the not the what we can say a physical quantity that has the same value for both. That is nothing but temperature.